I'm not used to using the microphone, so I apologize. I also apologize, my iPad did not connect. So I sent this version just before I left, and so I have the confusing situation of all the little tweaks to the talk that I made while I was here are now gone. So I usually appear confused, but I might appear more confused than usual today for that reason. So I apologize. So I'm the third talk on BE stars. One could wonder what is left to say, but I will try to say a few little things. I probably come from a very different focus than the other two talks, so maybe it'll be a little bit different. So I put up classical BE stars there because there are Herbig BE stars that have dust and are forming stellar systems, which I work on a little bit, but I won't talk about those today. I've given at the first line just the definition, sorry, I'm going to get used to this, of BE stars as rapidly rotating main sequence B stars that have shown H-alpha in emission at least once. And the beauty of this definition is it's a purely observational definition, which is great. It doesn't have any theory built into it. Even the main sequence is an observational fact in the HR diagram, so we just have an observational definition of what a BE star is supposed to be. So lots of work over many decades have given a physical idea of what BE stars are, and I think the physical idea is they're rapidly rotating stars. And I have critical in brackets here. There is a limit to how fast stars can rotate. It's often called the breakup limit, but that's not a very good word. If you spin a star fast enough, the material at the equator is going to go faster and faster, and eventually it's going to rotate the star. And that's the critical rotation speed, the speed at which the equatorial rotation speed is the orbital speed. That's very handy if you want to eject material into a disk, because it makes the delta V you need to do that quite small, which is useful. So we have main sequence stars surrounded by a thin equatorial Keplerian decretion disk that transports angular momentum outward via viscous forces, as Alex told us yesterday. You see the word decretion here. I guess where does that word come from? Well, we have accretion disks, which are studied endlessly in astronomy, and I guess we want to avoid the term excretion disk, so I believe that's the origin of the term decretion disk. And so this is a nice sort of theoretical summary. So how do we go from here to there? And the answer is, it's spectroscopy, right? It's all spectroscopy. When I was a graduate student, you kind of wonder, why do I study astronomy? And I think the first thing I really enjoyed was the connection between the small and the large. You go up in the night sky and kind of look at it, most of what you see follows from the physics of hydrogen atoms, which is a mind-boggling thing if you really kind of think about it, on how much of the universe is just set by the quantum mechanics of the hydrogen atom. But I think the next thing that really fascinated me was spectroscopy, right? The universe is big, things are far away, most sources are unresolved points of light. How do we know anything about their internal structure? Oh, it comes from spectroscopy. That's not quite true for BE stars. They are close and, most importantly, bright enough for interferometric observations to physically resolve the disk as an object of a resolved patch of light in the sky. But that was kind of a latecomer to this idea, and it's still quite difficult. The other thing I just wanted to briefly mention is, Alex pointed out the strange mystical world of the B stars. They encompass a huge range of temperatures and sort of physics, and why is that? Well, again, it goes back to, it's always best to define things observationally, and B stars are just main sequence stars that show helium absorption lines, but not helium ionized helium. And that just physical definition encompasses this huge range of masses and temperatures. The B stars are very interesting spectral type. You get radiatively driven winds that develop maybe around B2. And of course, if someone asks you what type of stars you're working on, you can confidently say, I'm working on the ones that explode, which makes them interesting. But that's only for the more massive of the B star range. There's one other little thing I want to mention about BE stars, is this phenomena of having this disk does leak out on the hot side and the cool side of the B star range. So there really are classical AE stars. Herbig AE stars, which again are pre-main sequence objects, they're forming stars, are very common. But there are, we believe, classical AE stars, so they go cooler than the B stars. And there are a very small population of OE stars, so these are much hotter or hotter stars on the spectral sequence, where we also believe that we have these sorts of disks. And I'll talk a little bit about the AE stars because I have a student working on them at this moment. So we have to show a spectra, and of course, I pick one of these AE stars. So very nice for representative A0 AE stars from the Lamos Data Release 5 series, very nice spectra. And it's going from about 4,000 angstroms right out into the red here at 8,000 angstroms. And you can see there's a reasonable label of the various lines and the emission lines. There's H alpha. We talk endlessly about H alpha, and I believe very good explanation was given yesterday on why the optical depth in H alpha is large. And so if you look at the star being surrounded by a disk on the sky, you might ask, why does the disk sort of end at whatever apparent distance it ends at? And that's because the H alpha optical depth at that point drops below 1. Right? So the optical depth is very important in setting the apparent size of the disk. So there's H alpha in emission. You can see H beta with a little emission feature, but there's lots of other features of iron, magnesium 2, which I'll talk a little bit about. Some of the passion lines are in emission. You get calcium, ionized calcium lines. So a very rich spectrum for these objects. Spectroscopy. Anyone who tells anyone they're doing spectroscopy, you're immediately hit with the first one, which is the tagline of turning rainbows into graphs for 200 years, which makes it sound like a pretty dull pursuit. But I really like the second definition, which is once we have those graphs, we turn them into three-dimensional pictures of the emitting region, which is an amazing thing. I don't have a BE star here. When I was a postdoc, I worked on AGNs for a number of years. AGN specters are very kind of bewildering, particularly if you're coming from stellar spectra. There's a very large range, and you get a lot of emission lines, a range of line widths from 1,000 to several thousand kilometers, a bizarre mix of ionization stages. If you look at some of these objects, there's neon 5, and remember the brackets around the name means it's a forbidden transition. So you're only expecting that in a very low density plasma. But, you know, you're getting some lower ionization stuff here. Here's H beta, for example. Somewhere in here is magnesium 2. So that's basically what you have. These objects are very far away. It's hard to get a resolved picture of what the interior of these objects that make these spectra might look like. And this is kind of the picture that is determined entirely spectroscopically, right? I worked a lot on the broadline region. The broadline region is where lines like H beta, for example, is supposed to have formed. So you have clouds moving at very high velocities around the central black hole that are emitting these lines. But there's this just very complicated geometry that was all worked out spectroscopically. It's amazing if you really think about it. In any event, I don't want to dwell on that. Everyone knows spectral classification. And here we see the various spectral types. There's the B spectral type. One thing this picture makes clear is stars show absorption line spectra, which I'm pretty sure everybody here is comfortable with, but if you stopped a person on the street and asked them what type of spectrum the sun should show, you'd probably get an emission line spectrum. It is, after all, a hot, glowing ball of gas, so you might expect there to be emission lines. And of course, there's not. And why do we get absorption lines in stellar spectra? It simply has to do with when we look into the atmosphere, how far we get to look depends on the optical depth of that wavelength. So how far in we can see, which depends on the opacity of the material. Energy is coming out of a star, which means it has to have a temperature gradient, so the temperature is falling with height. So if you look far from line center of a particular atom or ion's transition, you can see deep, but of course it's hot there. And in a star, there's no, you don't run out of optical depth, right? It's an infinite optical path back into the star, so you can never see through it. So you just see to hotter and hotter and deeper layers. But if you look close to the center of a transition, you're suddenly looking much shallower in the atmosphere. And so you're seeing a reflection of the temperature gradient. I have the expression for optical depth kind of written down here. The reason I mention it is because it's one of the defining features of being an astronomer is to make sure you have as confusing and counterintuitive notation as humanly possible. All started off in the wrong path thousands of years ago when Hipparchus decided the brightest objects in the sky would be assigned the smallest numbers. We never recovered from that basic fact. If you look at what optical depth is, if your medium has some geometric length L, and the critical thing for a photon, if I'm in this emitting plasma and I emit a photon, what might I want to know about it? Well, I'd want to know its mean free path, right? How far does it propagate between interactions? And that's what I call this little L lambda here. Depends very strongly on the frequency or the wavelength of the light. However, we cannot accept this, right? Mean free path, it's just too easy to know what that means, right? It's not obscure enough for astronomy. So astronomers take 1 over the mean free path and it defines something which everyone has heard of called opacity. So astronomers talk endlessly about opacity. So if I let a photon go and it has a tiny mean free path, it has a huge opacity. And if it has a big mean free path, it has a tiny opacity. So can you see how we get the astronomy vibe right away? That big things are mapped into tiny things and tiny things are mapped into big things. We're doing well. Here's an example, another sort of triumph of spectroscopy in astrophysics. This is the solar temperature distribution in the sun for a 1D model. It's very important to recognize this is a 1D model. So the base of the photosphere is here, and way up here is the corona. This line here is the inferred temperature distribution in the sun. This is height, and it's typical to set the height in the solar atmosphere is 0 at sort of the base of the photosphere. So the height increases as you move out of the photosphere. And all of these different symbols here are telling you what spectral feature was tweaked in order to match observations by tweaking the temperature. So the temperature was all kind of empirically determined from spectroscopy. And an example here is given by the very famous calcium, well, H and K. We just see the calcium K line here, a wavelength of around 4,000 angstroms. So the declining temperature with height that gives rise to absorption lines is just this little part here. So when we're in the wing of over here, where the opacity is low, we can see deep. We see the Planck function way down here, which has a higher temperature. As we move towards line center, the opacity increases, unit optical depth moves to higher H. We see a cooler temperature. And so this line is just a map of the temperature in the solar atmosphere. And you can see in the sun is not in radiated equilibrium. At least the outer atmosphere is not. That just means that you would think it would be in radiated equilibrium. All of the energy is generated in the core of the sun, the inner 10%, and it's just transported and redistributed in frequency as it moves outward. But no energy is created, no net energy is created or absorbed. And you would expect a falling temperature gradient to get the flux that would transport the solar luminosity out. But once you reach a temperature minimum, we think the magnetic activity of the sun does lead to heating, and it breaks radiated equilibrium, and that's why you get this temperature reversal. And so you can see the temperature reversal right here in spectral feature, that maps into the temperature minimum in the sun, right here. And then there's a reversal. There's emission in this core of this line, and it's simply following the temperature rise in the chromosphere. And so we see that directly. Of course, it falls again, and there's a radiative transfer reason for this fall. If the densities are large enough, you typically will see the thermal reservoir, the Planck function at each depth. But as you move out of the sun, it becomes more and more rarefied. And the local creation rate of photons is sort of dominated by scattering, and light can suddenly escape. And that causes this to decouple from the temperature distribution, and so you don't track the temperature anymore. But so a very nice way to produce emission lines. But if you look in the sun, you really have to look closely to see emission. I did a little picture of just what the opacity actually is, what it looks like for a reasonable gas in the universe. It's a function of the temperature. I think I've chosen 10,000 degrees. And the density, I think I chose 10 to the 12 particles. So the opacity, which determines the optical depth, depends on the physical conditions of the gas where you are. And it also depends very, very strongly on the wavelength. So this is the total opacity, and it's got some broadly varying parts, and it's got some steep spikes. And it's a sum of various sources. The first one is photoionization, where the photon interacts with an atom and then removes the electron. And that has to have a certain amount of energy or more, and that process will work. So you get photoionization from the ground state, n equals 1 of hydrogen, of the second state, the third, etc. So they're producing these opacity jumps. Photoionization is very important for the BE disk modeling that I do, because that's the main energy source into the disk. It's photoionizing radiation from the central star. But that's not the only. You can have discrete transitions within atoms. And so you can see the opacity for various transitions in hydrogen. So here's H alpha. It's very narrow. It's very narrow because you have to have sort of exactly the right energy in order to do that transition in hydrogen. And so Lyman alpha, the first, the n equals 1 to 2 jump is here. There's 2 to 3, the Paschen series, etc. So they're all a bunch of very narrow features. So you sum that in. There's also free emission, or Bremsstrahlung. You can think about that as electrons changing are free, so they're not bound to the nucleus, but they're changing between one hyperbolic orbit and another and exchanging energy. And then there's scattering. Scattering tends to dominate discussions at radiative transfer, but I won't talk too much about that today. And then you just sum them all up, and you get the total opacity. So we'll come back to that. So BE stars have a rotating disk. Why do we know there's a rotating disk? Well, we've got very good explanations yesterday. Essentially, the interplay between the constant contours of radial velocity on the plane of the sky and the Doppler shift. The classic example of a rotating object is a rotating star, and you get rotational broadening of the spectral lines, which I just want to briefly look at on the next slide. The other thing that I found interesting is, of course, the Doppler effect is used here. It's the Doppler effect that makes all of this possible. And I was, sorry, I'm having trouble with the controller, very interested to read the plaque that's just outside this room, in that Doppler was born in Salzburg. So at the very end of that plaque, it says, one of the most important tools in astronomy. Yeah, I'd probably say it's like the most important tool in astronomy. It has an amazing application. So if you look at, this is a little bit of math, but don't worry about this. I'll need a few of these concepts a little later. Here we have our classical spherical star. It has a rotation axis, so it's spinning around with angular velocity omega. And we're asking how each point on the surface rotates. Now, we're actually not interested in that for what we see. What we're interested in is the projection of that velocity along the line of sight to the observer. So here we have the observer infinitely far away in the z-axis. So if you look at what the v is, go back, it's an omega cross r, it doesn't matter. But if you look at Vz, take the projection of that, and then ask what the contours of constant radial velocity look like, it works out kind of amazingly. It just works out to strips on the projected spherical outline of the star. So everything in this strip has the same radial velocity. So by the Doppler effect, they're all shifted to a unique position in the spectral line. And this is why we can kind of get positional information from unresolved objects using spectroscopy, right? There's a correlation between the macroscopic position in the object and the radial velocity. And our spectral line gives us a little one-dimensional map of those emitting regions. And that's why we can reconstruct the geometry of the emitting region from this. So this can make a little rotation profile. The details here aren't important, but it gives the overall picture of what a rotationally broadened spectral line will look like just by summing up the areas in these particular strips. This has a neat application. We talked about Doppler tomography. I'm old enough to remember this. Does anyone remember Doppler imaging? It's still a huge field in astronomy. If you want an explanation of how to do astronomy, how to write a great paper, here's a great paper. They wanted to explain how we can use the correlation between position and velocity in a spectral line to map the surface of an unresolved star. So how did they do that? Well, the first object author was Vogt, so he wrote his name on the surface of a star, and here's the sort of little outline showing the inclination of the star. His name is here, but we're not seeing the one that he wrote. We're seeing the one that recovered. So if you use that little strip argument that I gave in the previous slide, and I sum them all up, you see there's going to be little bits that are different, right? It's going to be bright, 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 and then this dark bit is going to be a subtraction from that area, and that's going to make a little bump in the line. As the object rotates, you're going to see different versions of this name, and it's just going to give a time series of little wiggles in the spectra. And so what do you see? You see the wiggles in the spectra as a time series. You know about that nifty trick with the strips on the surface of the star, and you solve an inverse problem. And so this is actually the recovered. So his name is written very clearly on the surface of the star, but he rediscovered his name by analyzing the time series of the spectra. So it's sort of amazing. Very unphysical, right? It really is a very, there's either an element that's on or off on the stellar surface. And the other thing is, be a little bit careful. If you're wondering how was there enough information, sorry, I'm not using the microphone properly, in order to recover the name, the answer is there wasn't, right? This problem is underdetermined. And so you need to supply kind of additional information in order to solve the equations that you got. And so you're doing something like maximizing entropy or maximizing smoothness. Those are all mathematical constraints, and you can end up in trouble. You should try to make physical constraints when you're doing these sorts of problems. Mathematical constraints can lead to issues. This is a very interesting paper. If you're worried about those sort of things, I would suspect you check out. You can do the same thing for a BE star disk. This is made with my code, BE Ray. I'm using helium-1 6678, and I've got a filter. So I've got the spectral line, it's an emission line, but I've tuned a very narrow filter to be 200 kilometers per second to the blue of line center, and then looking at what emits in that band. You get emission everywhere because there's continuous emission, photoionization, recombination, free emission. But you can clearly see emission in the line. One reason I like this picture is you can see the line on the surface of the star, right? This is one of those strips we were just talking about. And this band is this line Doppler shifted by the star's rotation to that position. And so again, in this situation, you see this strong correlation between radial velocity due to either the star's rotation or the disk's rotation, and position in the object, which is why we can be fairly confident that the spectral lines that we see, the double peak lines that we see, are coming from a rotating disk in the way that we saw yesterday. So how is an image like that computed? You have to calculate the opacity because you have to calculate the optical depths. I have a little classic back of the envelope, poorly drawn picture of how this works. But here's the cartoon version. You have your star, which has sort of a photospheric spectrum. You're surrounded by a rotating disk. You need to solve the radiative transfer equation. Light propagates in straight lines, so you need a whole bunch of straight lines pointed at your distant observer. You calculate the opacity and the optical depths along each of these rays. You need the temperature and the density. You might need a bit more. I won't discuss that today, but it should be noted. And you also need boundary conditions, right? The transfer equation is a differential equation, and so you need to pose the boundary condition. And that's actually quite important in this model. These rays go right through the disk, but they go to the blackness of space. So the boundary condition is 0. A ray like this goes through the disk, but ends up in the star. So what is the boundary condition? It's the photospheric absorption spectrum that I showed previously. So if you sum up the contribution of all of these rays, you can actually make an unresolved spectrum of the object, the spectral line. But if you look previously, sorry, I wanted to go back, on the wrong thing. You can see the pixelated nature of this picture. So I've got all these little boxes. There's a ray coming straight out at you along which I've solved the transfer equation, and that's where the picture comes from. So getting the temperature is tricky. As I said, the heating in the disk that you have to balance heating and cooling in order to figure out the temperature. The heating is all coming from the central star and its photoionizing radiation field. That might not be the whole contribution for, say, the AE stars, but it certainly is for the VE stars. And then following, if I've managed to calculate this temperature distribution, I have the temperature and the density. There are details I'm not explaining here. Let's just go with temperature and density. I have enough to calculate the opacity and the optical depths, and so I can make either unresolved spectral lines, as I've shown here, or an actual image of the system. And so I've given some examples of the spectral lines that I've computed. A temperature distribution for the star 1 Del in a little bit more detail is shown here. I have a very simple density model. So it's important to contrast what I'm doing with what Alex is doing, for example. So Alex is kind of the Ferrari that's out there, has a lot more physics than I do. I'm sort of the person that's kind of, you've overlooked that dairy, I'm plowing the fields out there, basically. So I have a very simple density model. There's an overall scaling for the density. There's how fast it drops in the equatorial plane. There's a scale height for how the density drops as you go above and below the equatorial plane. And these are just treated as parameters. And so I can produce a huge number of models by just varying these parameters. So when I'm calculating things, I'm calculating thousands and thousands and thousands of these line profiles and then looking for the ones that best reproduce the observations. And so for each of these choices, I have to go in and calculate the temperature in the disk, which I've shown here. This is just temperature in Kelvin, how far away I are from the central star, which is rotationally distorted in this particular case. And here's the two-dimensional temperature structure. So my models are axisymmetric, right? So they're symmetric around the rotation axis. One puzzling little thing is there's an inner cool region in these disks. You go hot is red and cool is blue. And you have this inner region that's cool, which seems very odd. But there's kind of an analogy. I got to enjoy a solar eclipse a little while ago. And I was actually in the path of totality, which meant I was in the umbral shadow, which means if I look towards the sun, every possible path is blocked, right? That's the darkest part of the shadow. It's kind of a similar thing here. What's happening is that if I want to look back at the star, I have to look through the disk. But every path that I can look through the disk back to the star has significant optical depth, because this density is largest close to the star and in the equatorial plane. And so I'm sort of in a shielded region, but by optical depth. And that means that the amount of photoionizing radiation that that reaches me at that point is less than one might expect. And that's the main source of heating. So there's a dampening of heating. There still can be cooling, which leads to this cooling region. as you move farther away, just like in an umbral shadow, there's going to be a point at which not all path back to the star will be obscured, and so you get heating. So this is a typical way that the temperature distributions in these disks look. You get this inner cool region, you get these hot sheets on top and below where the density is still large enough to have significant heating due to photoionization. The disks are also very thin. I've always surprised by that. You have this scale height, and there's this very nice result that the scale height, the sort of characteristic, I'm not enjoying this clicker very much as it's easy to end up in the wrong place. The ratio of the scale height to where you are in the disk is roughly the sound speed at that point in the gas compared to the Keplerian rotation speed. Sort of a nifty result. The sound speed in this gas is about 10 kilometers a second, but the orbital speed is 100 kilometers per second, and that leads to very thin disks. And this is based on just hydrostatic equilibrium, the same thing for the Earth's atmosphere. The pressure gradient has to hold up the weight of the gas above me. And so here, there is always, at any point in this disk, there's going to be kind of a vertical component of the star's gravity, and that's what your the pressure gradient is supporting against you in the vertical direction. Of course, in the radial direction, what's the support? Well, it's in Keplerian rotation, so it's rotationally supported. It's the same reason the Earth doesn't fall into the sun. It's exactly the same explanation. So, why a thin disk? It's another sort of interesting thing. The idea that the disks were thin went back to polarization. So if you want a tough spectroscopic problem, polarization is one of the most difficult ones. Is that even a thing? Does anyone know anyone who tries to do polarization? I guess maybe it's so difficult. Yeah, but your instrument wants to polarize them. So polarization means the electric field of the light has a preferred direction. Your instrument wants to do that, and it's even worse because the interstellar medium wants to do that too. But if you're very careful, you can figure out that the light from BE stars is polarized at a surprisingly high level. It can be up to maybe 1% or 2%, which is very large for astronomical sources. And that immediately tells you that the distribution of material can't be spherical, because you wouldn't see that high level of polarization if it was. And so that immediately suggests that it's a disk. Now we have direct interferometric observations of these disks, which we know constrains them to be very thin. But there's also a very simple spectroscopic signature of this, and that is shell stars. So we talk about emission lines in H alpha, but there's a class of stars that have very deep central emission, or central absorption cores. So the central absorption is deeper than you would have expected just if you removed the disk and looked at the photospheric absorption line. It's actually deeper than that. And so the idea is simply you're looking through the disk and you're getting absorption of the photospheric light along the line of sight. That only happens, as I said, if the disks are thin. You have to be looking at exactly the correct direction. You know, the rotation axis has to be nearly in the plane of the sky in order to do that. And so these are called shell stars. Again, it's an observational thing. You do not need a theoretical explanation for them. They're simply a class of objects. And so 1 Delphini is a shell star. You can see how low. So the continuum has been placed at 1 here. The depth of H alpha as the photospheric absorption line might go to here, and you have this central feature that's even deeper than that, and that's thought to be absorption due to the disk. So the statistics of shell stars, plus how you expect the distribution of viewing inclinations to be set on the sky, suggests that the disks have to be very thin in order to account for the observed fraction of shell stars. So kind of a neat argument. That's purely spectroscopic. So what do I do? Well, I have these parameters in my density, my very simple density model. So n and rho naught. I have the parameters for the central star. I have how I look at the system, either edge on or pole on. And I have the extent of the disk, so I have an outer radius for the disk. Well, I can just pick a whole pile of H-alpha line profiles and start seeing if I can reproduce them, right? And so this is an example. It's a little bit hard to see, but the dots, so these are all one of many, about 100 BE stars that I fit here. The circles are the observations, and the solid lines are my fits by varying those parameters. So I have to have effectively a mass, a radius, and a luminosity for the central star. That gives me its effective temperature, its gravity. I may want to rotate the star to induce gravitational darkening, which I'll talk about in a few minutes. But the disk is parameterized by that overall density, that power law index, how big it is, and how I see it. And so you can extract all of these parameters. So you can get very good fits. My code can only do symmetric. You can't have V over R variations because the disk is axisymmetric. But within that constraint, you can get reasonably good fits. You can produce things like this, which show you the distribution in the density and power law index plane. These circles are different sizes because the disks are of different sizes. And this is something I've thought about in connection with binaries, right? I'm aware of the downturn in the sets, suggesting the disks are truncated by a binary. And I will eventually have a student in September begin to look if this is strongly correlated with the presence of a binary. However, this isn't that satisfying, and it's an interesting tale. These are parameters in a model, and the parameters only have meaning within the context of that model. These aren't, for example, a solution to the hydrodynamic equations where you have the physical quantities on a grid or something like that. So you could ask, how do I connect, or how can I make sort of model-independent statements from the spectra that I'm analyzing? And so, as I suggested, the disk sizes was an interesting one. We've already talked about that in connection with binarity. But I got very interested in the inclination. And the reason being is, sorry, these slides are slightly out of order from what I remember now because I'm using an old version. So I'll just jump ahead and jump back. So we have our massive stars are born in clusters, right? And so we've talked a little bit about the large fraction of BE stars that can be in clusters. And there was a paper a couple of years ago that said that there was a strong alignment between the orientation of stellar spins in clusters. And so I just want to, again, I apologize, this is a little bit out of order. And I apologize for them using theta for the inclination angle, it should be I. But you have an observer, and then your inclination angle is just the angle that the rotation axis makes with the line of sight. So if the disk is edge on, and they've got it defined the opposite way that astronomy, no, sorry, I have that, sorry. They have it defined the correct way. So if theta or I is 0, that means the rotation axis is pointing directly at you, and the disk is in the plane of the sky. And there are no Doppler shifts associated with the disk's motion. If I is 90 degrees, then it's the opposite case, that you're looking through the disk back to the star, and you might expect those shell stars to be occurring at that higher inclination. And if you take a bunch of stars and throw them randomly in a cluster with no preferred direction for the rotation axis, so there's no correlation at all, and then you say, I look at that cluster, what distribution would I expect for these angles? I don't think it's too difficult to believe that it's the sine I distribution, right? And so one easy way to see this is I throw them up there, and then I'm looking at it at a particular direction. What are the odds a rotation axis is pointing directly at me, right? That's essentially 0, right? And so the idea that these random axes would end up pointing at me is very small. And we know that sine I is 0 when the argument is very small. So sine I captures this basic idea. And the most probable location is, of course, with the rotation axis being in the plane of the sky. And you can easily make that mathematically definite by considering the solid angle of this little blue object. But you expect, if you were able to figure out the inclinations of a whole bunch of stars, and you made a histogram, you would expect it to follow the sine I distribution, if the spins of the stars in that cluster were random. And so, some work was done. It's based on astroseismology. I won't explain how it works, and I think there's reasonable skepticism that it doesn't work properly, and this result is a bit of an artifact. But it was very interesting. And they got, it seemed very lucky. The expected distribution is this step, which is supposed to be the sine I distribution, and the distribution they got for the inclination axes, these are old open clusters that have red giants in them, so the astroseismology was applied to the red giants to get the inclination axis. They certainly did not find the sine I distribution. In fact, they got very lucky. This correlation is easy to detect if in a low chance case that they're pointing directly at you, because you would have expected very few stars at those inclinations, right? This wouldn't have been a result if by magic the inclination were pointing, or the rotation axis were more in the plane of the sky, where you would have expected many stars anyway. So this was highly statistically significant and a very interesting result, right? Our B stars are all born in clusters, so we've taken something that has many, tens or hundreds of parsecs in extent of a gas cloud, collapsed it down. Even if you start with the galactic, differential rotation, you're going to get a little spin of that cloud that is amplified as it collapses. You have to parse out all of that angular momentum. And it's not inconceivable, it's not known really how that works. It's over such a large scale, and the transport of angular momentum is a difficult problem. A lot of it could end up in the individual stellar spins, leading to a high level of correlation. And that would tell us something important about how stars and clusters form. So this was a pretty interesting result. BE stars allow you to kind of work on this problem, right? Because you have this very strong correlation with the morphology of the profile, in this case H alpha, with the viewing inclination. And so if you look face on, you get a single peak. There are no Doppler shifts. The disk is spinning in the plane of the sky. If you look at an intermediate angle, then you get the pictures we saw yesterday, those patterns of constant radial velocity in the sky. So we can simply add up the area effectively in those contours, and we very naturally get a doubly peaked emission line. And then we get those shell profiles that I talked about. If you're looking through the disk, you get these absorption features in the center of the line. And so you might think that just by looking at H alpha, you could recover the stellar inclination quite easily. And that turns out to be the case. If you look at how, I'm not discussing the astroseismology case, but there was kind of a simpler way to do this based on time series, based on spectral time series. So for example, I've got a magnetic star written on top. So you can do spectral polarimetry and notice that the magnetic field, say along the line of sight, has a periodic variation. In these sorts of stars, these upper main sequence stars, the fields are simply frozen in. And so the variation has to reflect the rotation period of the star. So immediately it's a win. We know how long it takes the star to go around once. If we have some idea of how the radius of the star is, then its equatorial velocity is easy to calculate. If we know the viewing inclination, then we can form V sine I. But we know V sine I isn't observable, right? You can just go look at the broadening of spectral lines and get V sine I directly from observations. And so you can invert this argument and get sine I from the fitting value of V sine I from spectra, and then this V equatorial that comes from this time series. And so you can try to figure out if these inclination angles are randomly distributed or not. It historically has been quite difficult. If you look at this, this is number of stars. This is from an old paper by Helmut Abt. Number of stars, and then if you look at sine I, it just doesn't seem right because the numbers go higher than 1. But this is an error-prone procedure, and it's trying to account for the expectation given reasonable errors in the quantities that would need to be assumed. And he was looking for a preferential alignment of rotation axis, which he did not find. This has been done again very precisely in a similar way using time series measurements of V sine I in a number of galactic open clusters. Very similar plot. Does not find for many plots a high degree of correlation between the rotation axis. But this is all based on the star, right? It's all based on a time series and knowing something about the star and the measurement of V sine I. My method is a little bit different in that I'm really just depending on the properties of the disk, right? I'm using the morphology, the emission morphology of H alpha in order to infer the inclination angle. So all you really need to get the inclination angle is, one reasonable H alpha profile of modest resolution and single to noise. You could ask if this works, and I have tested the BE star method quite carefully, and it's a good segue because we really have resolved images, sort of BE stars on the sky via optical interferometry. My colleague Chris Teisner at Central Michigan University is the expert in interferometry. So here, it's an optical interferometry, and it predominantly works at H alpha because, again, the high opacity in H alpha makes the disk a big object on the sky, relatively speaking, and so it can be resolved. The baselines here between the various telescopes are maybe 100 meters. And so you can just resolve things that are maybe a milliarc second or so on the sky. And so this whole setup is just wild, right? If you think about how this thing works. It's a Michelson interferometer. And so you have to take the light from the star, introduce a path difference, and coherently recombine the light to get an interference pattern. This is done at optical wavelengths. So you could say, what's the big deal? I've seen the movie Contact, et cetera, et cetera. The VLA has been doing this for years, right? There's no big deal here. Well, the frequencies of radio waves are much, much lower, and they can be converted into electrical signals. For visible light, you can't do that. And so if you look at how the light is recombined here, it's all done literally with evacuated tubes, right, and mirrors. It's absolutely wild, at least to me, that this can be made to work at all. The basic idea of how this works is you coherently interfere the light. It's a Michelson, interferometer. So if the star was a point source on the sky, you get a nice sine interference pattern. You'd be perfectly bright, and then in between the bright fringes, it would be perfectly dark. And so that contrast between the bright and the dark is called the fringe visibility. This is amplitude interferometry. And so an unresolved point of light in the sky has a visibility of 1. But if the object can be resolved by the distance between the telescopes in this instrument, you'll have a resolved object on the sky, and the constructive interference will not be as perfect because you'll have several emitting points on the surface. And so the visibility will get less, and the visibility will drop from 1. So if you had a perfectly resolved object on the sky, you'd end up with a visibility of 0. And so that's what these look like. And so this is a couple of very common or well-known BE stars, Omicron Aquarii and 48 Persei. This is spatial frequencies. So this is just the distance between the telescope and its orientation as projected on the sky. Then you do your interference measurement, measure the visibility of the interference pattern, and then wait for the sky to turn in order to change what that projected orientation and size of the baseline is on the sky. And so you can map out this visibility as a function of spatial frequency. I don't know, that is a two-dimensional pattern on the sky, but it's very confusing to look at pictures like this. So typically you just fold them in. If you look at 48 Persei, for example, this dotted line here that starts at 1 and then just drops a little bit below 1 at the largest spatial frequency, that's what we expect from the star, right? We get definitely way below that because we have the added contribution of the disk on the sky. And so in this case, my code, as we saw with the picture previously, can produce an image of what the object will look like on the sky, but I wanted to do something that was completely independent of my code. So I simply chose a very simple model for the visibilities, like a little top hat function for the central star. And this is a Gaussian disk of major axis A, minor axis B, and then some position angle on the sky. And I simply add them together. There's a certain fraction that's assigned to the central star, and then a certain fraction assigned to the disk. So you're modeling it as a little sort of bright bit, circular bit for the star, surrounded by an elliptical disk on the sky. One could ask why you see an elliptical disk. Despite what we were told yesterday, I made the assumption that the disk is circular, and that the reason we would see an elliptical disk is because of the projection angle I. And so I simply recover the viewing angle of the system from the ratio of the minor to major axis. And so you do that for a small number of stars on the sky, because there's only a small number of objects that are both close. In order for this to work, one might wonder how interferometry overcomes the seeing limit imposed by the Earth's atmosphere. Everyone knows just basic seeing on the sky limits you to an arcsecond or so. Well, you take the observations very quickly within the coherence time of the atmosphere you're looking through, and that means you have to have incredibly bright objects in order for this to work. And so that's why I'm an astronomer who works on stars that have names, right? Those are bright objects that they have names. So a little bit of a confusing plot. Let's just look at the one from Omicron Aquarii. Here's the axial ratio I got from interferometry. The reason there's a cluster of dots is if you look at this previous plot, there's a large error bar on each of these observations of the visibility. So it's a Monte Carlo simulation. You just realize the data within the errors, refit the data, and look at the distribution of the fitted parameters. So each one of those dots is one of these Monte Carlo realizations of the interferometric data. The big dot there is sort of the median value that you get from the interferometry. This histogram on the right, the right side, is the fitting from H alpha that I get as a histogram. And so you can see that you're agreeing reasonably well with this is purely spectroscopy based on the morphology of H alpha. This is purely interferometric based on geometric models of the light in the sky. There's no relationship between these two calculations at all. And in almost all cases, it works reasonably well. I like this picture because it kind of shows the errors and everything. You never have a scientific result. X is not a scientific result. X plus delta X is the scientific result. So I like having the errors. But this gives you the correlation between these two methods with R's of about 0.9. So it seems to work in a small sample really well. Another interesting thing you can do is, I'm surprised this worked out. If you fit an elliptical model to the light in the sky, you get a position angle. The scattering of light, you expect the plane of polarization to be perpendicular to the disk. So polarization gives you the vector perpendicular to the disk. Interferometry gives me the vector along the disk. I simply rotate that by 90 degrees and see if it agrees, as it should. And it does. If you look at this, this sort of hashed region here is the position angle determined by interferometry within the errors. So the kind of the width of the fan tells you the error in the measurement. And then the dotted line gives the polarization angle. So I've rotated the position angle by 90 degrees. And in almost all cases, it agrees very well. Of course, in some cases, this does not agree very well. One might wonder what you would make of that. I would emphasize how hard reducing the polarization data is, right? It's not trivial. And you really need to correct the polarization from the star by the polarization introduced by the interstellar medium as the light travels. So I am thinking that is an error in the polarization data, but it's not something I've checked. I should really look into that. Is there any other way I can figure out that these inclinations work? And another thing we were introduced to in VE stars is the rapid rotation of the central star and gravitational darkening. So I have from my own code, this is just the central star, there's no disk. I'm rotating, I think, at 90% of the critical velocity. It's sort of leaning toward you. I think the inclination angle is 60 degrees. And this is intensity, but I could have converted this into temperature, so the white and yellow would be hot, the dark would be cool. And it shows you that as you spin the star more rapidly, the temperature is not a constant across the surface, and the object becomes oblate. It's actually reasonably easy to understand how that works. I apologize. Goes back eventually to the temperature gradient. Remember when we started and we looked at the sun, the depth of the absorption lines was controlled by the temperature gradient. If you look at a rotate, so imagine the star wasn't rotating. You'd have the radial distance from the center, and that would define sort of the surfaces of constant potential, right? It would just be spherical shells centered on the origin. If you put in rotation, you're going to spin about an axis, you're going to modify the potential in the equatorial plane, but you're not going to modify the potential surfaces near the poles. And so the potentials move farther apart in the equatorial plane, but don't move at all. And that means effectively, because the temperature is determined only by the equipotential surface you're on, they spread out in the equatorial regions. But if they spread out, that means the temperature gradient is less. But what does that mean? The flux being transported is less because it's controlled by the temperature gradient. And so the system very naturally darkens. That's why you get gravitational darkening. Tricky thing, I believe this is with a slightly more physically realistic treatment. And this was all worked out by von Zeipel in sort of the 1920s. There hasn't been too much done to the theory since then, but a little bit. And as we know, there are direct observations of rotationally distorted stars. So we talked about Arachne already. So this is a definite effect. What does this do for me? This means that what you see in your spectrum is determined by the inclination angle in part, right? Even if it's just a photospheric spectrum. Because now it's not as simple as saying, well, this is a 20,000 degree effective temperature B star. I have to account for the effective temperature variation over the surface. And I have to do that strict thing and add them all up with the correct temperatures, etc. And so if you think you took enough spectroscopy and did enough modeling, you could back out the inclination you were probably looking at this rotationally distorted star. And this has been done. Zurich in 2017, 2016 did this. So this is on BE stars, but there's really not a disk around these stars. He's modeling the photospheric spectrum and figuring out what that sort of distortion and distribution of effective temperature across the surface has to be, and what angle do I need to be viewing that at in order to most accurately reproduce the photospheric spectrum. Tricky, but you can do it. And for this sample, I have about 100 stars in common with this sample of Zurich from 2017. He can back out the inclination angle from the star. I can back it out from the disk. How do they agree? I had the, sorry, this is a change that I made in the talk. I had just the H alpha inclination versus the gravitational darkening inclination originally, and it kind of looks like a mess. But I realized what you really need to do is ask the right question, and the correct question to ask is, are the differences consistent with 0 within the errors? And if you do that, that's what this plot is. So I'm subtracting the inclination I get from H alpha minus the one from gravitational darkening, given the errors in both methods, and plotting it versus the inclination angle that I get from H alpha. And it went from, this is a mess, I don't think it worked, to, uh-oh, I wonder if someone will view this as being suspicious, right? Because if you look, these are all, I haven't shown the errors, but they're all 1 sigma. And so you would expect this to agree with 0 and 1 sigma in 68% of the cases, and it turns out to be exactly 68% of the cases. So it worked out very well. There are some systematic problems at lower and small, inclinations which are small and inclinations which are larger, but this method works. And completely different calculations, right? One is based on the star, and one is based on the disk, and it works very well. This is something I had taken out, but I think it's good that I left it in. I really enjoyed the talk yesterday afternoon about the deep sky spectra, very impressive. And I really enjoyed the fact that looked up those classic line ratio diagnostics and backed out the classic astrophysics, right? And so it's interesting, if you're not a professional astronomer, how you might interact with more sophisticated calculations. And I had a PhD student who was interested in machine learning, as all graduate students are nowadays. And so he asked me one day if he could train a neural network in order to back out these inclinations, right? So you could ask, what does that do? Like, I have models, you can run the code and get the inclination. But there is a real advantage to that, right? What does the neural network, what's the input to this black box? It's really just the normalized H-alpha line profile cut out in a box, sampled at, 30 kilometers a second. You give those relative fluxes to the box, and this is a regression neural network. It spits out the inclination for you. So it's a very direct connection. It's sort of an interpolation method through what is quite a complicated calculation. It takes sort of directly what you would produce at the spectrograph. You give it to this object, and it gives you sort of the answer based on the models that you would expect from a more complicated modeling. And this sort of thing, neural networks are very portable now. There's standards on how you should store them and read them and implement them. And so this is one possible way that in the future you might be able to interact with quite sophisticated calculations. The producers can train neural networks on using the direct observed product in order to get to the answer. Lots of interesting details, but I don't want to go through that now. So, one thing you could ask is, for these field stars, we went through and said, are the inclinations, you'll expect a sine I distribution on sky, right, for just random objects. And if you work this out, either using the H-alpha inclinations or the gravitational inclinations, this is a known problem. It was recognized maybe 20 years ago now that there's a lack of high inclination objects. Weird. Like, you'd like to come up with some awesome explanation for this. Like, the spins of field stars are correlated with the galactic plane. And it's one of those things that you have to be careful of, because you can just close your eyes and say, yeah, that's totally got to be true, right? Because of, how does the spin in these molecular clouds happen? It's because of the differential rotation of the galaxy. Oh, that's absolutely got to be true. Chances are it's absolutely not true. My guess is this is a selection effect. And so it's one of the reasons why I don't have any specific cluster results for this method at this moment, is my graduate student is going through what the, so in order to apply this to an observed sample, that observed sample has been selected in some particular way. It's sort of going away now. I mean, now we're sort of in the era of, let's just take the spectra of every bright object in the sky, like that's the plan. But previously that was really not feasible, and so you had to select out candidates, which stars are most likely to be VE stars. And you have to implement some method to select candidates which you target for spectroscopic follow-up. And my guess is that this sort of thing is a result of that. It's not as simple as I thought it was going to turn out to be, which is why I don't have any results today. But we need to nail down that bias in order to use this method in order to precisely say whether or not they're correlated spins in clusters. Because if you allow this sort of bias in, so for example, I can fit this with a preferred direction in the sky for the rotation axis and get a number, right? But I might not believe that number is true because really I'm just fitting the bias, I'm not fitting the actual object. And this bottom graph is just a cumulative distribution. It's easier to see this terms. This is just a test to show a difference between the two methods. This is the shell parameter. The shell parameter is when you see one of those shell lines, you measure the height of the peaks and you divide it by the depth of the central absorption that you see. And if that number is bigger than about 1.5, for technical reasons I won't discuss, you think you're looking, it's defined to be a shell star. And as I said, you expect shell stars to be seen at high inclination. And so if you look at, this is the threshold for an object to be a shell star. So you expect anything above this line to be seen at high inclination. And you see that the heat-alpha method works, as you would probably expect, works extremely well for that. But the gravitational darkening method has trouble with that. That it will assign objects that from the emission absorption spectrum of H-alpha you would think has to be a shell star, but it's given it at an intermediate inclination where it seems inconceivable that you're looking through a disk. It's kind of a technical point. One thing you can do, getting inclinations are kind of interesting because it's a fundamental parameter of the system. Cosmology has this awesome term called nuisance parameter, which is a parameter in your model which you must have but you do not care about. You often integrate over it to get rid of it or something. Inclination often provides a nuisance parameter. If you could fix it, you don't have to vary over it. So if you're fitting these rotationally, gravitationally darkened models, if you could fix the inclination angle, you would have one fewer parameter in order to vary. Another nice thing you can do with the inclination angle is you can back out the equatorial velocity of the star from the V sin I measurement. And this is what I've done here, but I have not measured the V sin I's that I use here. And so you're getting the equatorial rotation velocity as a function of spectral type. And I put in two lines to guide the eye. One is that critical velocity where the material in the inner edge of the disk would orbit. And then the dashed line is 80% of that. We saw the 80% number come up in Alex's talk. And I've done that for 2 points on the main sequence. These two solid curves are for the zero age main sequence, and the dashed curves are for the terminal age main sequence. If you think about how stars evolve on the main sequence, for all but the highest masses here, they evolve at a constant mass but expand. And so that means that their critical rotation values go down. And so if you look at this picture, it's one of those things, right? Every field has the one animating idea that has sort of guided the field. And this goes back, Struve, one of the Struve, produced a paper in the 30s pointing out that the magic sauce in VE stars is critical rotation. And it just doesn't seem to work out as you might expect. Wonder why critical rotation is so important. It's because we were told that pulsation is almost certainly the mechanism behind ejecting this material. Pulsation is a hydrodynamical acoustic phenomena in the atmosphere. What sort of speeds do these pulsations generate? Well, there's only one characteristic speed, that's called the sound speed. You're not going to get many multiples of that out of the hydrodynamical process. But the gap between a subcritically rotating star and the critically first orbit could be huge compared to the available velocity boost, even if you're in the direction of rotation. So ejecting that disk becomes much, much easier the faster the star is to critical rotation. And so it tends to be a little bit of a block. I've noticed some really embarrassing stars down here, which I believe are just errors in the V sin I. So you have to take this picture with a grain of salt. But it is nice that it is something that you can do. You can talk directly about the equatorial velocities. You don't need to work only in projected values and then make some assumption about the projection. Don't need that. So I was thinking about this, and all of these V sin I's are corrected for gravitational darkening. And the idea there is, remember we go back to that strip, that star with the strips that we saw at the very beginning, with those strips being lines of constant radius. What if at the outer edge of each of those strips, I made that strip darker and darker and darker? its contribution to the total line would be less and less and less, right? But if you think about it, we got that classic correlation between rotation speed via the Doppler effect and position. So you have the fastest rotating part of the star contributing much less light than you would have expected. And that means that if you don't know about this effect, you can underestimate the widths of the lines, right? And that's what this this sort of counterintuitive figure does. This is what happens when you let theorists make a figure. You get this kind of complicated one. But that's the basic idea, that the widths of the line will saturate because as the star rotates faster and faster, the highest moving bits of the star are becoming fainter and fainter and fainter, so you don't see them. So there's a systematic stalling of the width of the line that even if you rotate the star faster and faster, the line doesn't get any wider. So you need to know about this. This is an old result, and this was problem solved, right? This takes care of the whole problem. All BE stars are critically rotators now, because obviously we forgot about this effect, and when we introduce this effect, all BE stars are going to be near critically rotating and sort of Bob's your uncle in terms of the ejection mechanism. That didn't really work out the way it was planned. It's certainly a very important physical effect, but even accounting for this, you don't make all BE stars near critically rotators. So I've often wondered about that. And another thing, we touched a little bit about this in terms of rotation. The sun generates its energy by the proton-proton chain in its center. These B stars are hotter, and so they can use the CNO cycle. So it still converts 4 hydrogen into helium, but it does it via reactions involving carbon, nitrogen, and oxygen. One thing that process does is it changes the abundances of carbon, nitrogen, and oxygen in the core. And the biggest effect is in nitrogen. It makes it more abundant than you would have expected. So the first thing is, who cares? You don't see the core of the star. It just makes no difference whatsoever. You don't have to worry about this. Well, if you spin the star very rapidly, you might imagine you can mix some of that material to the photosphere. So very difficult physical process in order to model. It's a diffusive process and it's an advective process. You have to treat all these things correctly. Often this mixing is treated purely as diffusion, which can often be correct. Nadir has this wonderful example of how diffusion can be. Diffusion is something that takes places where you have a lot of it and randomly transports it to places where there isn't a lot of it by random processes. And he uses the example, well, there's a huge inequality in wealth, in money around the world. And there is in no sense that money is diffused across the world, right? The world just does not work like that. So treating these processes is quite difficult. But anyhow, I've actually in BE stars looked for enhanced nitrogen, photospheric nitrogen abundances using the NEAM survey, which was a magnetic survey, but had a lot of BE stars. When you do really careful studies of abundances, there's actually quite a tight concentration. It's remarkably small around the solar abundances. But when I did it, these aren't big numbers, but I kind of got this population of low nitrogen abundance objects, which is totally not what you would have expected, right? You might have expected them all just to agree with the other BE stars, but no. And we worked really hard to try to figure out everything that could have gone wrong. And the only thing that, in retrospect, I could have thought that went wrong was that I included emission from the disk, right? The disk is going to, at the minimum, put in a continuum. So if you're looking at your stellar photospheric spectrum, there's going to be an additional continuum contribution from the disk. That's going to dilute the lines, right? So it's going to make them less strong than you would have expected. And that will lower the abundances. But that effect has been included in this measurement. But one thing I didn't include was emission in the lines. And it's kind of interesting to look at that. The first thing, you might say, look, you're crazy. You're not going to know emission in the line. Well, you just look at the line, right? Not a complicated problem. You either have emission in the line or you don't. The issue there is you're kind of trained on hydrogen lines. Hydrogen lines are very broad. they're much broader than the rotational broadening of the star or the disk. And a simple explanation is these hydrogen atoms exist in a plasma in the stellar atmosphere, and there's a constantly evolving electric field in the position of this atom. And that changes the energy levels. Hydrogen is particularly sensitive to that. You could statistically say is not a rotation profile has been ejected from the sample. And what you're left with at higher disk density is narrower lines that imply smaller V fracs. But again, all of these points are statistically consistent with a rotation profile. So this is just something I was doing in the fall before my teaching load as a university professor kicked in the spring term. I didn't have much time to do research. So there's lots of details to look at this. My guess is this will turn out to be kind of like gravitational darkening, that in some particular cases it will be very important, but it might not explain the full picture. It might not make all the E stars critically rotating objects. In any event, I've rambled on for long enough. There's my takeaway, but I don't think my takeaways are particularly useful in this case. I'd like to thank my students, my colleagues, and particularly my funding. And I apologize if I went over time. I was a bit discombobulated by a different slideshow than the one I had prepared. So thank you. Oh, sorry. Any other questions?
Yeah, there are questions. Yeah, but let them
let
people read it. Take out.
Do you need a microphone?
I'll try to speak.
I think they're
a
fine.
simple question, but how does the time-dependent variation you get in the accretion disk affect your ability to interpret the inclination from the profile of the disk?
Well, that's an interesting case. And I mean, one of the things when I published that paper, the initial one with the interferometry, et cetera, was, well, you've picked these lines at particular times and you got these particular values, just pick them at other times and you'll get different values. But I ran that experiment. My colleague Chris Teisner, for all of those objects, has a complete database of, he's very careful, he gets H-alpha spectra in every interferometric observing run. So there's a matched H-alpha spectra with every one of those points. So at some of those stars, the disk went away during the 5 or 6 years. Each of those plots are maybe a couple of years of observations, and so you've got to make sure you combine only observations where the disk is similar. But blah, blah, blah. In any event, I went through and I fit time series of H-alpha spectra where the disk was, for example, in Kappa Drac, I believe, was just going away. You fit it, you get the density in the disk is decreasing, the H-alpha emission is obviously decreasing due to that reduced density, but the inclination is always the same, right? So the inclination, that information persists in the profile. I had a little animated movie showing how the line responds to all of the profiles, but the non-functioning of my iPad made that not viable.
Could you show the slide on that you showed the correlation with UV data?
Yes, there.
Yeah, that's very nice. That's very nice paper, by the way. This 2020.
Yeah.
Just a quick comment. If I'm not mistaken, Uding made a survey in polarization, but he didn't make an attempt to remove the cell polarization.
No, it's beautiful. Yeah. His method is really clever.
Isn't it?
Yeah, but
this much maybe the fact that it doesn't account for it.
Well, if you look at how we did the interstellar, if I remember the paper correctly, it was in 2000. I read it a number of years ago. My understanding was, so Jupiter is our VE star. These are other stars in the field at different distances that we don't expect to be polarized. So we measure all the stars in the field. Hipparchus had occurred. We have good distances in each of the stars. He made a curve of growth of polarization.
Yes.
Yeah, so that That resists,
That's
okay.
He used an old catalog from
Yeah,
IES.
yeah.
Right?
Yeah.
The only problem is that these, most of these targets are more than a degree away.
Yeah. So,
And
it's,
therefore,
yeah.
it's not mapping exactly.
That's
So
right.
it's a very clever idea.
It is
works for some stars,
Yeah.
but it doesn't work for others.
My only idea on that, I don't know if anyone's done this, but it's certainly something that's possible. There are very accurate dust maps available for the Milky Way. So I've often thought to go back and interpolate the dust column density to each target and compare with the interstellar polars to see if there was a strong correlation.
There is.
Oh, someone has done
Yeah,
it. Awesome.
yeah.
Could you send me that paper?
Sure,
Because
yeah.
it's in my file folder of stuff for undergraduate
That could
students.
be-
So,
that's
yeah.
good.
I suspected it was, but I couldn't find it.
Okay.
So, yeah. But you're exactly right. Those are super difficult. It's a hard problem to do that.
Can you show the slide with your theoretical profiles which change with the inclination? Why is this strong central peak at the inclination of 20 degrees?
This
That wine bottle.
The wine bottle
Yeah,
shape?
so why is
I believe that Hanashek has a paper explaining that particular type. So it's a fact that you have not separated the two peaks. They still over. I can't explain it off the top of
But then
my
there are
head, but
two
that's
shoulders,
an expect. Back in the old days, that was used as an argument for a two-component emitting region, one giving the wide
Yeah.
component. But no, that follows directly from the geometry. Like if you just do a simple, there are particles that emit photons in Kepler, and you will get that effect. I can't describe it off the top of my head, but and in fact, I know the paper. So.
And the other question is that you are trying, I mean, United students probably trying to figure out the extents of the disk. So there was another slide before that.
Yeah, I've often had that in.
Yeah. Okay. You know that disks appear and disappear.
Yeah.
When they start developing, the extent cannot be the maximum.
That's right, yeah.
So how do you take it?
Yeah, the answer is, I don't know.
Yeah.
We'd have to look up and look at the history. It's not a large number of objects. The total number of objects is 100, so we can look at the historical record of each of those objects and try to, 100 is at least large enough that if you pare down the sample a bit, you might be left with something. Again, it's in my file folder of stuff for undergraduate thesis projects, so, but it's one of those things where, it's one of those parameters that might mean something. Like you're sitting there thinking, you're writing your research grant thinking, I got to connect this with planets somehow, right? I've just got to connect it with planets.
Yeah.
And so I've often wondered if that would be a possible. The other thing about the disk truncation is it always is truncating at sort of the Lagrange point between the two stars. There's not like, I guess, yeah, we'll talk. I'll talk later. I don't want to
separate.
bore people. Yeah.
I got it.
Are there any other questions?
You had several slides with Gray as the reference.
Yeah,
Who?
that's Dave Gray. He's at my department. He wrote a very well-known textbook,
Yes.
The Observation and Analysis of Stellar Photospheres. Unfortunately, he passed away 1 year ago, quite suddenly. But yeah, it's Dave's book. It's a classic book if you're interested in, particularly if you are observing sort of classical. Dave describes what Dave does.